Hello. Thank you very much for giving me the opportunity to be just once a movie star instead of a teacher. I'll take this opportunity to introduce this classroom where I used to teach for 7 years in a row, and where I still teach from time to time when I just want to remember why I left for. This is a genuine Princeton University Physics Department t-shirt which my son brought me when he entered Princeton University. Let me tell you about this lesson, how will it go. Some of you asked me to do the demo video of physics lessons, and some of you asked me to do the demo version video of a mathematics lesson. I thought, why not do them both at the same time? Because anyway, this is the way I think it should be done. For those of you interested in physics, the lesson will be about the work done by a force. And for those of you interested in mathematics, the lesson will be about the integral of a function. The level of the lesson will be somehow higher than usual, and also the durations could be somehow longer. But please rest assured that once at your schools, I will stick only to math or only to physics if you want, and only to the levels you choose and the textbooks you choose. But for now, being here, I will choose to do something more special because I like to brag and to show off. And first of all, you must see exactly what you are paying for. So let's start with the definition of the work. Consider a trajectory of a point like body. This is the body. Let's call its mass m. The position of the body with respect to a reference frame. R. And its velocity tangent to the trajectory. V. A force is acting on the body like that. The angle between the force and the velocity will be alpha. For defining the work done by the force, we need a very small, a very tiny displacement, an infinitely small displacement. So, being infinitely small, you can see it. But I will choose to draw one, just a small vector on the sketch. This one, dr. Of course, dr equals velocity times a very small, an infinitely small amount of time. By definition, the work dw equals the dot product between the force and the displacement. So the units for work, the standard unit, are the standard unit of force times the standard unit of displacement, that is Newton times meter, and it's called Joule, symbol J. There are two ways to calculate the dot product. One would be to use the magnitude of those two vectors. I mean dW equals the magnitude of the force times the magnitude of the displacement times the cosine of their angle. And the other one, using components on the axis, on the three-axis, dW equals the component of the force on x-axis times the displacement on the x-axis plus the component of the force on the y-axis times the displacement on the y-axis plus the same for the z-axis. We will use both of them, but mainly the first one. There are two cases here. There's a general case and the most simple particular case. We'll start, of course, with the particular case. If the force acting on the body is constant, in this case, we can take into account many such small, very small displacements, and the force is acting always the same. So in the end, the whole work will be calculated doing the sum of all these elementary works here. I mean, W, the work, will be the force times the first displacement plus the force times the second displacement plus and so on. The force is a common factor here times the sum of all the displacement, which is the force times the whole displacement, which we call delta R. Let's say that this is delta R from the beginning till the end. Let us take an example here for this particular case. Let's say we have a body at the surface of the Earth. This is the surface of the Earth. This is a body of mass m. The force of interest here will be the gravitational force Fg. We don't denote the weight of the body with W because it's already taken. We'll call it gravitational force instead of weight. Let's say that this body is an aerobics pilot and he takes off and do some stunts in the air. One more stunt? Okay, just one more. And in the end, its position will be here. So the displacement will be this one, delta R, and the angle between them, alpha, is this. Please observe the supplement of the angle alpha. Let's call it beta, which gives us right triangle here. This is a 90 degrees angle. Also, let's call the height of the pilot at that moment h. So, if we use the first method of calculating the dot product, we get the work done by the gravitational force as being equal to the gravitational force times the magnitude of the displacement times the cosine of alpha. Or, if we take into account that the cosine of the supplement of alpha is equal to minus the cosine of alpha, then we get the work of the gravitational force equals minus Fg times the magnitude of the displacement times the cosine of beta. Look in the triangle and please observe that the cosine of beta equals h over the magnitude of the displacement, and introducing the cosine in the formula here, you get the work of the gravitational force. The displacement cancels and you get minus the mass of the pilot times the gravitational acceleration times h. So as you can see, this expression here does not depend on the stance the pilot does, but only on the final height of the pilot with respect to the initial level of this one. To take into account this height and only this, we will need just a vertical axis, let's call it the y-axis. We will consider the origin of the axis somewhere deep inside the Earth, in the center of the Earth. You will see why we'll do this. So the first level, the initial level where the pilot starts, is exactly r, where r is the radius of the Earth. And the final position here will be, of course, r plus h. Well, let's put in some values, some numbers, and do the math here. Let's consider the weight of the pilot to be 1000 newtons. Sorry. The weight. 1000 newtons, that's a little bit too much here. It's not like a pilot, it's more like me. Remember, 1000 newtons, I must do something about this. And quick. So I have to do a stunt here. Well, let's say h equals 1 meter. I mean jumping on the desk or something. But even better, let's say half a meter. Because I am afraid of height. So in this case, the work done by the force of gravitation will be 1000 newtons times 0.5 meters equals 500 joules. Minus, of course, minus 500 joules. Well, let's try to give a graphic interpretation of this value. So I said that it doesn't count whether the trajectory is straight up or anything else. So I'll put a diagram representing the gravitational force with respect to the position on the y-axis, starting at r and finishing at R plus H, the force is already constant, so the diagram looks like this. This is 1000 newtons. And you get a rectangle whose length will be exactly h equals 0.5 meters. So when you do the multiplication here, you get an area, the area of the rectangle, which is the magnitude of this work. I mean, the magnitude, the modulus of this value. If you want to take into account the sign, the minus, then you must use the other way of calculating the dot product. I mean, instead of taking the value of the gravitational force, you must use the unit vector of the y-axis and write that the gravitational force is minus 1000 J, where J is the unit vector of the y-axis. In this case, the diagram will look like this. This time I will call it Fy, not Fj, because it's a component here. The value will be minus 1000 newtons. And the area will be the same, but this time being under the y-axis, we'll say that this area is minus 5000 joules. Well, as you can see, this particular case is really straightforward. So will be much more interesting to take into discussion the general case where F is not a constant force. General case, F not constant. Let's say that the force, depending on y, looks like something like this. I'll say that it's the component, and the force increases and decreases, something like this, from some y, initial y, to some final y. Y initial, y final. For every part of this diagram, if we consider just a very small displacement, let's say from here to here, let's call it dy, we can say that the force is almost constant. There is a slight slope here, but being so narrow, this strip, we can say that it is a rectangle and that this area here is exactly dy times the force corresponding to that particular y. And if we do this for all these small displacements, which are an infinite number of displacements, starting with the first displacement here, then the next, and finishing with the last displacement here, we conclude that the area under the diagram means exactly the work done by the component Fy of the force on the y direction. How can one calculate such an area? Well, this is where the integral enters into play. We will take the case exactly of the gravitational force, because in the end it is not constant. The surface of the Earth, it is not like this, it is like this. And the gravitational acceleration of a body is not a constant g equals 9.8 meters per square second. Instead, g for some y. Now you can see why I choose to consider the origin of the axis in the center of the Earth. Because y here means exactly the distance from the center of the Earth to the point we start. So this one, you know from another lesson, that is equal to j times r over y all squared. Or, to see even better, is j times r squared times 1 over y squared. So we'll have to do the diagram of this function multiplied by the mass of the body. I mean m times g of y, which looks something like this. That's the value 9.8 meters per square second at the surface of the Earth. And this one is the value at h, at the height h, times the mass here. And it means that this area under the graph is the magnitude of the work done by the gravitational force. Of course, if you want to get also the sign here, you will have to use, instead of the magnitude of g, the component on the y-axis. I mean, taking the graph as being negative, as we did before, and the area will be just the same, but negative in that case. We'll stick to that because we can put the sign in the end. So, how can we calculate such an area here? Well, we must divide the displacement from r to r plus h into many very small displacements. If the number of these displacements tends to infinity, there will be exactly some infinitely small displacements, and we can work effectively, we can work the area from this. Let's say the divisions are like this. They do not need to be equal. I call them y1, y2, y3, yn minus 1. The last one, which is exactly L plus h, I will call it yn. And there is also the first one, r, which is y0. And for each of them, I will calculate, instead of calculating exactly the area of this strip, or the other one, I will take the area of a rectangle. Here it counts the fact that the function is not constant, because now the displacement here, although it's very small because there are very many such small displacement, it doesn't tend to zero. So if we take always the value at the left of the displacement, I mean starting with the value at the surface of the Earth, we will get for the first displacement this area here until down on the axis. For the second one, this area also till the axis, and so on for the last one, this area here. As you can see, there are some small portions which makes that the sum of this small area be greater than root it, what we want to calculate. Let's write down this sum. Let's write it like this. S1 equals m for gravitational acceleration for y0 times y1 minus y0 plus mass times gravitational acceleration for y1 times y2 minus y1 plus so on, mass times g for y n minus 1 times y n minus y n minus 1. Of course, we can write down this expressing the function g for every y corresponding. I mean mg r squared times 1 over y0 squared times y1 minus y0 plus so on mg r squared 1 over yn minus 1 squared times yn minus yn minus 1. Also we can use the sigma symbol for the sum, and the constant will be a common factor in front of the sum. That's mass times g times r squared, sigma for k starting from 0 to n minus 1, 1 over yk times yk plus 1 minus yk. This sum is called a Riemann sum. On the other hand, we can do absolutely the same thing, but this time taking for each small displacement the value at the right of the displacement. I mean starting for the first displacement with this value at the right, j for the y1, and finishing for the last displacement here with the value for r plus h. The expression will be almost the same. I can write it down. I can call it S2 like m j for y1 times y1 minus y0 plus so on, mass times j for yn times yn minus yn minus 1, or using the radius of the Earth, mg r squared 1 over y1 squared times y1 minus y 0 plus so on mg r squared 1 over yn squared yn minus yn minus 1. And using the sigma symbol, it's mgr squared sigma for k equal 1 to n 1 over yk squared times yk minus 1. This sum is something smaller than the area we look. The first one was somehow greater. This one is somehow smaller. Why? Because we start with this value here and we continue with this one. So all this narrow strip here will be under the graph we look. For instance, if we took the simplest case, just n equal 1, then each sum will have just 1/3. S1 will be just mg r squared 1 over y n, let's say, but n is equal 1 times y n minus y0. There is just 1 and 0 because it's just one division here. But this one is the gravitational acceleration exactly at the surface of the Earth, because these two are equal, and so it's mj times h, because yn is r plus h in this case, y0 is r, so difference is exactly h. And the value of this sum is exactly this, the whole rectangle here, so it's way too great, this one. And the other one, S2, is mg r squared 1 over, this was y0 here, y1 squared yn minus 1 y0 again, but this time being y1 squared, it means that this is the gravitational acceleration in the end, right here, and this means that the area is the smaller possible, this one. Way too small. This is way too big, this is way too small. But now look what happens if we make n to be 2. N equal to, we'll have here two divisions, not necessarily equals, not necessarily in the middle, let's say closer to r, but it means that we'll take the first division just for some y here, and the second term, there will be two terms in S1 and two terms in S2, will be this one. So from the big rectangle here, we take off this rectangle, so it still is greater than what we are looking for, but not so great. And if n equals 3, will be even closer to what we are looking. The same goes for S2. We'll take the first value of R of G here, but only until here. And the second one will be the final gravitational acceleration. So we get one more rectangle here. So the area will be a little bit bigger than before. It was this area, and now it's also this one. So it comes in the end, getting n equal 3, 4 and so on, this one will get bigger and bigger and will tend also to the same value. So we have two sums here, and the greater is n, the more these two sums, this one is decreasing and the other one is increasing, and they will get the same result in the end, and is the result we are looking for. How can we get this result? Well, let's take the first sum, for instance. I'm sorry, I don't have it anymore, I must write it once again. It was mgr squared, sigma from k equal 1 equals 0 to n minus 1 over yk squared, yk plus 1 minus yk. Okay, so how can we calculate the sum of n terms like this? Well, we'll take another expression, this one, 1 over yk plus 1 over yk minus 1 over yk plus 1. Make this expression to have the same denominator, so it will be yk plus 1 minus yk over yk times yk plus 1. The numerator here is exactly the same as here. The denominator is somehow greater than this. Here it was yk squared. This is yk times yk plus 1 squared. So this expression here is not exactly this one, but when we'll take n to the limit of infinity, we'll see that practically it doesn't count. Why? Because if there are such small number of division here, an infinity number of division, every point of the segment here will count as a y, and two consecutive y's, yk and yk plus 1, will be almost the same. So we will see that this one can approximate by yk squared if n tends to infinity. So we can calculate this sum as being mgr squared sigma from k equals 0 to n minus 1 over yk minus 1 over yk plus 1. Let's write it down explicitly, I mean without using the symbol sigma. It's mgr squared 1 over y0 minus 1 over y1 plus 1 over y1 minus 1 over y2 plus so on 1 over yn minus 1 minus 1 over yn. All the intermediate terms cancel, and all we are left with is the first term and the last one. I mean S1 equals mgr squared 1 over y0 minus 1 over yn. And as you can see, it doesn't depend on n. We said that these two terms, these two factors here are almost equal if n tends to infinity, and in fact you can see this, that in the end is just, let's write it here. S1 equals mg r squared 1 over r minus 1 over r plus h. Without repeating the calculation, you can see that S2 can be written in the same manner, just like this. And again, when n tends to infinity, we will have many such terms, and 2 by 2 they will cancel with each other, and the result, of course, will be the same. So it's equals S2 in the end. So, as I said before, it means that this greater area here begins to decrease, and this smaller area here begins to increase, and in the end, the both of them are equal to exactly the area we are looking for, and it means that this is the work done by the force. But just wait a second here. Well, R was the initial y and R plus H was the final y. So the work of the gravitational force would be mg r squared 1 over y initial minus 1 over the final y. If we take outside a minus mg r squared, we get 1 over y final minus 1 over y initial. But what was the function? This one we have to calculate here. The function was, remember, I will write it again. The function was the gravitational force equals the mass times gravitational acceleration for a y. I mean m times the gravitational acceleration at the surface of the Earth of r squared over y squared. So these are constants, and the only function of interest here is f of y equals 1 over y squared. Now look what happens here. We get the minus, and instead of the function y over 1 over y squared, we get the function 1 over y. Now, as you know from the derivatives, the lesson of the related to the derivatives, the derivative of the function 1 over y is minus 1 over y squared. So this function we'll have to calculate the area here is the derivative of this function we got in the end. Well, this operation, which is practically the inverse of the derivation, it's called integral. And we can denote this one with the symbol like this. It's the integral from y initial to y final of mg r squared over y final dy. Or integral from y initial to y final of m times the gravitational acceleration is a function of y dy. And the result is exactly this. Is the integral, is the function which by derivation gives the function we are starting from. It's mg minus r squared 1 over y final minus 1 over y initial, and that means equal to minus mg at y final or times y final minus m gravitational acceleration at y initial times y initial. And this is how one gets to define the integral of a function as being the area between the graph of this function and the axis. Of course, do not forget that for us this work should be negative. We took it here just in the module, but as you saw in the first example, when the force was constant, the diagram must be under the axis, so the sign will change here, but that's not important for the definition. Well, I'm sorry if it took a little longer for this lesson. Hope you enjoyed, and hope to see you soon somewhere in China. Bye bye.